I'm going to talk about rotational kinematics equations. I'm also going to talk about how to convert between angular and linear versions of two kinematics equations. So first, let me list the kinematics equations I'm going to be focusing on. Okay, so if you have motion that has a constant angular acceleration, then the following equations apply. Okay, let's be clear. Theta is the polar coordinate angle variable. Omega naught, or omega sub 0, and omega sub f represent the initial and final angular velocities. Alpha represents the angular acceleration, and t represents time. Now, for specific problems, sometimes people are concerned that they won't be able to easily determine the best equation to use. So let me bring something to your attention that I think will help you in selecting the best kinematics equation to use. Notice that the first equation does not have omega final in it. The second equation does not have alpha. The third equation does not have delta theta. And the fourth equation does not have delta t. If you are trying to solve a problem and you don't know the value of a variable, then clearly you don't want to be using an equation that's going to expect you to know the value of that variable. So let that be your guide to select the correct equation, the easiest equation to use. Let's do some examples now. Suppose I walked up to a merry-go-round that was initially at rest, and I started spinning it so that it had an angular acceleration of 0.2 radians per second squared. And suppose I wanted to know the angle that the merry-go-round swept through in 1 minute. Okay, so let me write down the information that I just stated. So the merry-go-round was at rest, so that means the initial angular velocity was 0 radians per second. The angular acceleration, I said, was 0.2 radians per second squared. And I said that I wanted to know the angle swept through in 1 minute. So working with seconds, delta t is 60 seconds. And what I'm looking for is delta theta. Okay? We do not know what the final angular velocity is, nor do we care. So why don't we choose the equation that does not have omega final? So I'm going to use the first one. All right, so 0 times 60 plus 1/2 times 0.2 times 60 squared, that gives 0.1 times 3,600, or 360 radians. All right, let's do a related example. Suppose I did want to know what omega final was. How would we calculate omega final? Only using the information in black that I've written down on the board. Well, for that calculation, I would use the third kinematics equation. So delta omega equals alpha delta t. So omega final minus omega naught equals alpha delta t. We know that omega naught is 0, so omega final is simply the product of alpha and delta t, or 0.2 times 60, which gives 12. So 12 radians per second is the final angular velocity. All right? Now, let me have you try an example. Suppose that an ice skater was in a spin, and suppose she had an initial angular velocity of 3 radians per second. And also, suppose that she brought her arms in. You may know that if an ice skater in a spin brings her arms in, she increases her angular velocity. And let's say that after 5 seconds, her angular velocity was 6 radians per second. And let's say that that process of increasing her angular velocity took 5 seconds. Okay, I want to know what angle did she move through, did she spin through in those 5 seconds. So pause the video and try to calculate that, please. Okay, I'll go ahead and work it out. So we don't know, nor do we care, what alpha is. So a good choice would be the second kinematics equation. So this would give 3 plus 6 divided by 2 times 5, or 9 divided by 2 times 5, 45 divided by 2, so 22.5 radians. And I hope that's the answer you got. All right, let's do one more example and then we will move on to something else. Suppose there was a DVD player with a DVD in it, a movie, and it may or may not be a broken DVD player, but regardless, whether it's broken or not, the angular acceleration once it starts spinning the DVD is 3 radians per second squared. Okay, and it started from rest, so the initial angular velocity was 0 radians per second. Okay, and let's say that it does 5 revolutions. I want to know what is the final angular velocity after those 5 revolutions. So pause the video and try to calculate that now, please. Okay, I'll go ahead and do it. So I don't know, nor do I care, how much time this process took, so I'm going to go with the last kinematics equation. So omega final squared minus omega naught squared, or omega sub 0, whatever you want to call it. And omega naught 0 is 0, so the square of the final angular velocity is 2 alpha delta theta, the product of 2 alpha and delta theta. So omega final is the square root of 2 times alpha times delta theta, which is 2 times 3. And then for theta, for delta theta, we need to convert 5 revolutions to radians. 5 revolutions, you multiply 5 by 2 pi, and that'll give you 10 pi radians. Okay, now there is something you could put in your calculator, and if you do, you will get the answer of 13.7 radians per second. I hope that's what you got. All right. Now let me shift gears and talk about something else. Now, using omega in alpha, you can describe motion, the motion of an object in a circle. Now, that's not the only way to describe the motion of an object in a circle. What if we wanted to use or calculate the arc length that the object sweeps through in a certain amount of time? Okay? What if we further wanted to know the rate of change of the arc length for some unit of time? Okay, so that the rate of change of it, what the length of arc that an object is sweeping through, is if we define the arc length, if we represent the arc length by the variable s, then this is the rate of change of the arc length, delta s over delta t. That is referred to as the tangential component of the velocity. The units are meters per second, okay, just like motion in a straight line. Let me draw a picture and try to help you understand what this means. Okay, so let's suppose this blue object is moving along this black circle, okay, and so v sub t, the tangential component, will tell you how many meters per second, if that's the units that you're using, how many meters for every second that the blue objects moves along the circle. Okay? Now, at every instant, if the object kept traveling in the same direction that it was traveling for at that instant, it would move tangent to the circle. Okay, so we could call it an instantaneous velocity vector. Okay, now when the blue dot, when the blue object moves somewhere else, like down here, then the tangential velocity component is going to be like that, in that direction. Okay? So the point that I'm making is that for any instant, you can calculate a linear velocity and linear acceleration. Okay? Now, if the blue object is increasing its speed as it moves around the circle, then it would have a tangential acceleration component as well. So that would be in the same direction as the v sub t vector. Okay, so I can draw that as well. And what would be the definition of a sub t? Well, a sub t is the rate of change of v sub t. So I can write that formula this way. Okay, so let me repeat. Here we have the tangential velocity component and the tangential acceleration component. Okay, now let's see if we can relate these to omega and alpha. So we know that the length of an arc is equal to the product of the radius and the corresponding central angle. Okay, so that implies that delta S is equal to R times a corresponding delta theta for motion along a circle. All right, let me divide both sides by delta t. and the left side is equal to what I called v sub t, and the right side is r times the definition of omega. All right, so there is the relation between v sub t and omega. Now, let me work with the v sub t equation that I just put in a box. So that equation implies that the change in v sub t is equal to the product of r and the change in omega for an object moving in a circle. Okay, now let me divide both sides by delta t again. Hold on, let me recopy the equation. Or rewrite the equation, I mean. So delta Vt is equal to r times delta W. That's true for motion along a circle with a constant radius, constant r value. Okay. So now let me divide both sides by delta T. Okay. The left side is what I called a sub t, and the right side is r times the definition of alpha. Okay, so those are some important equations that you need to know. Now, let me relate the centripetal acceleration to omega. So you may recall that for motion, the motion of an object in a circle, you may recall that the centripetal acceleration is equal to v squared over r. I'm going to put a subscript t because that's what the v in the centripetal acceleration equation is. It's the tangential velocity component. Okay, so AC is equal to v squared over r. But we just determined that v sub t is equal to r times omega, so let's make that substitution. And so we can simplify that equation and we will get the following. Centripetal acceleration is equal to omega squared times r. Okay, so write all of these equations down and we will finish by doing some exercises. Okay? So I'll do this one. Suppose an object is moving in a circle with an angular velocity of 5 radians per second, and suppose the radius of the circle that the object is moving on is 10 meters. So what is the tangential velocity component? That's the question I want to answer. Okay, I know that v sub t is equal to omega r. So for this situation, the object is moving in the circle with a speed of 50 meters per second. All right? Now let me have you do some examples. Suppose an object was moving on a circle with a speed with a tangential velocity component of 60 meters per second, and suppose the circle has a radius of 5 meters. Can you tell me what the angular velocity is? Okay, pause the video and try to solve that now. Okay, I'll go ahead and work it out. So, working with the equations I just listed, you can see that omega is v sub t divided by r, which is 60 divided by 5. So the angular velocity that I hope you got is 12 radians per second. Excuse me, 12 meters per second, right? Because we're not talking about... oh yeah, it is. Okay, we have to be careful to make sure we use the correct units. So for v sub t, it would be meters per second. And for angular velocity, it's going to be radians per second. All right, so let me do an example with a sub t, and then I'll have you do one last example. So suppose an object was moving in a circle with an angular acceleration of 7 radians per second squared, and suppose the circle had a radius of 2 meters. Can we determine a sub t for that example? Okay, so yes we can. I'll go ahead and work that out now. So we know that a sub t is equal to r times alpha, 2 times 7, so we would get 14 meters per second squared for this example. Okay? And now let me have you do an example. And actually, after you do an example, I want to do one more calculation. So would you please tell me the angular acceleration if a sub t was 3 radians per second squared for an object moving along a circle with a radius of 3 meters? All right, pause the video and see if you can calculate the angular acceleration. All right, I'll go ahead and do that now. So using the equations that I recently listed, you can see that alpha is a sub t divided by r, which gives 3 divided by 3, so the answer is 1 radian per second squared. And then the last example I want to do is an example of a centripetal acceleration calculation, and then I'll end. So suppose that an object was moving in a circle, and suppose all you knew was the angular velocity, 5 radians per second, let's say that's what it was, and you knew that the circle had a radius of 3 meters. Is that enough to calculate the centripetal acceleration? You might want to pause the video and take a crack at it. Okay? So I'll go ahead and calculate that. So we know that the centripetal acceleration is equal to omega squared r. So for this problem we get 5 squared times 3, or 25 times 3. So the answer is that the centripetal acceleration is 75 meters per second squared.